Bueno, gracias a todos por venir. Se supone que este es el ciclo de seminarios de la Facultad a cargo de la Secretaría de Ciencia y Técnica. Yo no tengo nada que ver con la Secretaría de Ciencia y Técnica, soy investigadora acá del observatorio nada más. Pero tengo el placer de tener de visitante a Víctor Cernic. Víctor es estudiante de la maestría en astronomía de la Universidad de San Pablo. Trabaja en el Instituto de Astronomía, Geofísica y Ciencias de la Atmósfera de la Universidad de San Pablo, bajo la dirección del doctor Laerte Sodré. Lleva 4 años trabajando con técnicas de Machine Learning, es miembro de la colaboración SCLAS, y lo que va a mostrar hoy en su charla es cómo aplica él las técnicas de Machine Learning a su trabajo sobre los datos de SCLAS, específicamente para los parámetros de poblaciones estelares. Víctor, gracias por venir y gracias por la charla.
Yo voy a hablar en inglés, pero pueden hacer preguntas en español, sin problemas. So, hi everyone, I am Victor. So I'm currently working with FlyRT, as Nadia said. And today I want to present to you very quickly what is S+, so the Southern Photometric Local Universe Survey, which I think there are a lot of people working here in La Plata with S+, in particular. And then I will show you for the rest of the presentation my application, so what I try to do with the S+ data. So let's start. So the Southern Photometric Local Universe Survey, S+, so it's a wide science survey which is located in the T80 telescope south, which is the one over here. The T80 was constructed basically for S+, and 90% of the time is devoted to observing S+, and 10% to the Chilean community. The S+ is a photometric survey. So most of you are familiar with photometric surveys, I think. Okay. So photometric surveys are basically a way to, instead of having a spectral survey that you have the information for each wavelength, you have the value of flux. Usually on photometric surveys, you have some distinct values for a flux integrated over some filters. So in the case of S+, we have a 12-band system. So it is all of the bands that you're seeing here are the 12 bands of S+, and we have the S+ as a 5-broadband system, which is the UGRIZ, which are the larger ones that you see. And it has 7 narrowband filters that are trying to get an idea of some spectral lines. So just to show you in a spectrum. So this is the S+ bands plotted for each one of its distinct spectral lines. So for example, this one is, this filter is trying to grasp the H alpha line, the calcium triplets, the H delta, and so, well, whatever you see here. And the ones that are not depicted, so the heavens and narrow, it's the ones that are broadband filters. So for example, this one, I think it's the red filter, if I'm not mistaken. But so each, there are 5 not named filters and 7 spectral lines one. And S+ is we cover a very large area of the sky. So these are the times of S+. I don't know when this was updated the last time, but we have observed, well, more than 2,600 tiles, and there are yet almost halfway to be observed. And S+, so I just want to give you a very quick explanation. But so the takeaway from this is that S+ is a 12-band photometric survey that is trying to cover a great area of the sky. The first, second, and third data releases are publicly available on the S+ Cloud website, which is the one that is depicted over here. It's very easy to use the website. We have some, you just need to create an account very quickly, and you can just start doing some SQLs to obtain data. And the DR4 is being used only by members of the S+ collaboration, but sorry? So if you want to use the 4th data release, I think you can talk to the coordinators to be included in the S+ collaboration if you want to use this data. And there are millions of objects that have been observed, and there are million more to come. So what to do with all this data? We have a lot of data, and what do we do with it? Well, I'm going to present now my work.
Which target are you
I will go to 0.1 redshift, and I'm just selecting galaxies. I work with galaxies, but I think that will be more clear throughout the presentation. Okay.
The limiting magnitude is 21. This means that the median redshift for galaxies is 24.
So are you able to know this band? Are you able to make photograph not to the spectral? You were able to estimate the frequency?
Yes. We have a team devoted to that to only study the spectroscopic redshift. Oh, sorry, the photometric redshift.
Yeah, when I saw you the bands and the broad bands and the narrow band.
This one?
Yes, I was thinking, and then you showed the other one with the characteristic of the spectrum. Yes, that would be for a nearby galaxy, but otherwise.
Yes, this is for start in the galaxy.
Yeah.
Of course, if you are looking for a galaxy, you are not looking at, say, the age of filter, for example. H alpha falls, the H alpha line falls into this filter up to a redshift, a very small redshift. After that, is redshifted outside the filter.
Yeah, that was my question. For why are you waiting?
Yeah, but this doesn't, you can anticipate the photometric galaxy. And with 12 band, it's very good accuracy. For example, in the case of SPS, with launch,
Yes.
You have an accuracy of 0.42. In the case of S+, we are able to improve it for 0.415. So we have a gain compared to SDF.
And I think that there are some people working with high redshifts even in S+. So Raquel is doing a
because F is magnitude limits. You have a few objects that are crazy that are very high redshift that are granted enough to be so there are people as we work this way, they find ways
It is that even though the spectral lines fall out of the filters, you still have some information that is useful for determining the redshift, even for high redshift objects. No problem. Okay, so I'll talk now about my work. So it's entitled Stellar Population Photometric Synthesis with AI of S+ galaxies. So the main general idea is that I'll try to obtain stellar population parameters from photometric synthesis of the S+ photometry using artificial intelligence. It's quite self-explanatory. So the main motivation behind this is, for example, how do we study galaxy parameters? How do we go from an image such as this one from Andromeda Galaxy to obtain the mass, age, metallicity of these objects? Usually, we do some kind of SED fitting, so spectral energy distribution fixing. The basic idea is that we need the spectrum to obtain these parameters. To obtain these parameters, and we can do this kind of SED fitting via only a few observations. So in this case, for example, I took from a paper that is trying to fit from a number of different surveys. So it has Spitzer data, it has HST and some other surveys data. and is trying to apply some kinds of STD fitting codes to obtain the spectrum of these objects over here. And we usually, when you work with STD fitting, you have to do some constraints. So you have to set, for example, the star formation history that you want, the metallicity, the range of metallicities that you want to study. You usually have some idea, you need to input some priors of the object that you want to study. And so the idea behind getting from the spectrum to the property is that the physical process that occurs inside the galaxy leaves some marks on its spectrum. So as a galaxy evolves, so does its spectrum. And so the idea is that by looking at the spectrum, you can get some grasp of the property, so the mass, the age, and the metallicity, by comparing it to other objects that we know. So, and this is a very well-known relationship. So there are a lot of STD fitting codes. For example, there are STARLIGHT, SIGALI, FADO. These are one of the bigger ones. There are bagpipes, there are prospector. There is the one that Fabio was talking about, the PPXF, which they use here. And so there are a lot of different STD fitting codes. But from what I showed before about S+, so it gets to the, you can have an idea of what a photometric pipeline would look like for a service such as S+. So you usually would get the photometry directly from the survey, for example, S+. Then you do some kind of STD fitting, so whatever code you choose to work with, and then you will get some properties. My idea is that, is it possible to obtain the properties directly from the photometry? Do not go from these, from the photometry to the STD to the properties. Try to go from the photometry directly to the properties without obtaining the spectrum in the meantime. And the advantage of that is not, is that usually STD fitting codes take some time to work. So it can take up to, when the last time that I was talking to someone that was working with Starlight, they told me that it took for like from 2 minutes up to 10 minutes to 20 minutes per galaxy to obtain a good fit. And this is kind of unacceptable. If you're working with S+ that has millions of objects, you need a lot of computational power to apply this STD fitting. So the idea is that by using machine learning, we can drive down the time needed to make this, to find this relationship, to obtain the properties a lot. And that's what we will try to do, to relate the photometry to the properties. So let's talk about the data. Just to summarize in a visual way, we are trying to solve this problem over here. We're trying to go from we have some features, we have some information that it's kind of the question that we want to ask to our model. We want to give it the 12 magnitudes from S+ that I described before, plus a value of redshift that we will be using the photometric redshifts. And we want the model to answer us some questions. So it gives us either some kind of parameter. So it can be the stellar mass, the age, the metallicity, the velocity dispersion, the reddening, the age alpha equivalent width, the star formation rate. I'm sorry, it's not the history, it's the star formation rate. But we want the model to kind of gives us something back. And so the idea is that we will train different models. Each model will be computing a different stellar population parameter, such as these ones. And since we are trying to use machine learning needs lots of data. So we need a large data set to make this thing work. And since S+ doesn't have a lot of objects and at least not robust observations from the stellar mass, the estimations from stellar mass, age, metallicity, we will train on a synthetic, robust data that was obtained from Starlight. And then we will train our model to apply it to real data, to S+ data. And so I think it will be clear once I show you how we're going to do this. So we're going to base our whole analysis on this data set that was created by Werley et al. 2019. So Ariel Werley, a group of collaborators, they managed to combine the SDSS spectra plus the galaxy photometry to obtain some very robust spectrums. And so they did it for 137,000 galaxies. They obtained they combined the galaxy photometry with the SDSS spectra. This made the UV emission much better, and this makes the parameter estimation much better as well. And so they managed to apply the STARLIGHT SD15 code through these spectrums. And we also use the spectroscopic redshift for our analysis. Even though we will be using the photometric redshifts when we apply to S+ data, just to train our model, we use a spectroscopic redshift. And so just to have an idea, what we have for 137,000 galaxies, we do have their spectrum, and we have their properties. So the mass, the age, the metallicity, whatever you want to obtain. And this is just a plot to show you what exactly our data right now is. So, this is a plot from Ariel Werner's work. And these are 3 different galaxies. So each galaxy has the red line is the SD fitting only based on the SDSS observation, so the SDSS spectrum. And the blue line is the SDSS plus galaxy photometry combined. So you can see that for everything above 4,000 angstroms, it's quite the same. So you don't see any change from the blue line to the red line. But everything before, so the blue region of the spectrum, you see that there is a very wide gap between the 2 of them. So you see that by adding the galaxy photometry, we have some better results, some better spectra. And these will make a very large difference when we talk about the parameters estimations. And so the idea is that we have some robust spectrum and some robust parameter estimations. What do we do with it? So the first thing that we need to do is that, remember, we want to find a relationship between the 12 magnitudes from S+ to the stellar population parameters. Since we have the spectrum, well, the first thing we need to do is just calculate the photometry. So that's what we did. We calculated what we call a synthetic photometry. Based on since we have the spectrum, we can just apply this relationship based on the S+ filters to obtain the magnitudes of each filter that would be observed if the object was observed by S+. And so now what we do have is for each galaxy, we calculate the magnitudes of the filters. And so we have for each one of them, the 12 magnitudes from S+, plus a value of redshift that comes from SDSS, plus all of the parameters that we want to estimate. Something else that we did, and this is very common for any type of for some synthetic photometric works. So usually what we do is that even though things should be equal, so our synthetic magnitudes should be similar to the S+ magnitudes, usually there are some errors or some considerations that make them, there is a slight offset. So we needed to do some calibration. So in these plots over here are showing for a cross match that we made between our data set, the 137,000 galaxies, and the whole S+ catalog, and we obtained about 7,000 objects that were cross-matched. And so we plotted over here for each filter. So these are just 3 of the 12 filters, the R, I, and Z. We plotted the observed magnitude, so the value directly from the telescope from the S+ survey, and the synthetic magnitudes that was calculated via this formula over here from the spectrum. And so we see that the first first result that we had were the contour lines. So all of those contour lines were, when we plotted, we saw that there was an offset. We want everything to be in the 1-to-1 line, meaning that the synthetic magnitude is equal to the observed magnitude. But we didn't see that. We saw there was an offset. So we need to correct that. We need to apply the relationships that are described in each plot, and to make sure that this offset is corrected and all of the synthetic photometry is calibrated. Okay, so let's see what we have right now. We have 135,000 objects. Each one of them has the 12 magnitudes plus a value of redshift, and then we want to correlate to find a relationship with a stellar population parameter. So the stellar age, mass, metallicity, and all the ones that I described before. And usually when we have that, we apply something called the supervised learning. So basically we have questions and the answers that we want to find. So we do have the features and the targets that we want to apply to our model. So we're going to use a supervised learning, and we're going to train, I think, 9 different models. Each one of them is going to obtain a different stellar population parameter. So there is one code for stellar mass, another code for age, metallicity, and so on. And we train. I mean, there are a lot of different supervised learning algorithms, and we needed to find out what are the best ones. So we try to make a grid of consider different algorithms, and the ones that we came up with were the most used ones. So the simplest one is linear regression. So basically trying to fit a line through our data, and then we use KNN regressor, random forest regressor, XGBoost, and finally neural networks. And we see that for the errors, so there are the root means per error. The root means per error is a notion of error of the data that the lesser the value, the better. So we want to minimize the root means per error, and we want to maximize the R squared, which is a value that goes from 0 to 1. And so we see that for both of our metrics, the neural networks presented the best results. So in the case of the neural networks, we had both the best root means per error and the R squared and the training time. So we also consider training time when taking these into account, because some models can take a lot of time to train. For example, the XGBoost model took about 30 minutes, so it wasn't feasible for us to optimize this model, since creating a grid of hyperparameters would take a long time, and 30 minutes is a lot of time for this problem that we wanted. So we consider the neural network, since in all of the cases that in all of the metrics that we considered, it was the best one. So just to visualize the architecture, I'm sorry for writing Portuguese here, but the idea of the network, I think most of you already seen some kind of figure like this. So this is an architecture of a neural network, and the input layer is the thing that we want to give the network. So we're going to give it a value of redshifts and the 12 values of magnitudes from the S+ telescope, from the S+ survey. And then after this layer, this input layer, we're going to go through 2 hidden layers, which are going to do the hard work for us and find the relations. This is where the actual machine learning part is going. And finally, we have an output layer, which is trying to estimate the stellar population parameter that we want. So remember, we have 9 different architectures like this. Each one of them is going to output a different stellar population parameters. And let's go to the results. So I think this is the main result that I want to show you, and I think this is the plot that I like the best. So these are the estimations, the predictions for 2 of the 9 parameters that we decided to use. So on the left side, we have the stellar mass parameter, and on the right side is the age weighted by flux. The weighting by flux is just a convention. So that's the way the starlight gives us, but basically it's the age of the galaxy, the stellar populations. And so what these plots are showing is that on the y-axis, we have a predicted value. So what the network, the neural network gave us from the magnitudes plus the value of redshift. And on the x-axis, we have a true value, which is the value directly from starlight that we are assuming is correct. And so you can see that, for example, for the stellar mass, we have almost all of the data above over the 1-to-1 line, which is the red dashed line over here. And that's what we want. We want the true value to be equal to the predicted value. We want our predictions to match the true value from starlight. In the case of the stellar mass, we have some very good results. We can see that the errors are very low, so 0.06 for the MAE, for example. And in the case of the age, we see that even though we have a larger scatter of the data of the predictions, we still see that the error itself is very low. So the error is very good our model. And so we are pretty happy with this result. This is the main result that I wanted to show you. And now I'm going to go through a few other, some analyses that we made, just to make sure that our results are robust. And so one of the things that we did was to analyze the redshift dependency. So let's consider, for example, for high redshift objects, maybe our errors are larger, or we wanted to see if there was some correlation between the redshift and the error. For distant galaxies, the error was higher, or something like that. And so this is a plot of in the case of the stellar mass. And the x-axis is the redshift, the y-axis is the error, the true value minus the predicted value, and in absolute values. And we see that there isn't quite anything that we see. There isn't like a straight line going up. For example, as the redshift gets higher, the error also gets higher. No, we see that's quite straight. But what we see here is that our model is only predicting for galaxies up to 0.1 redshift, which is okay if you're going to talk about the local universe. So, for example, in the case of hornets, I think the redshift of hornets is 0.04. Is that correct? 0.005, yes. So yeah, it falls into this range, and so you can reliably use our model for galaxies in hornets, for example. But if you want to apply it to anything above 0.1, you're going to end up with some problems. So what we want to do in the future is to increase the range of redshifts being used. And now, one of the things that we did was consider I talked about before, we are considering the redshifts when estimating the values. And we can see the impacts of the redshifts by just looking at two cases. Let's see the prediction of the network with redshift and without redshift. What happens when we consider both cases? And we see that, for example, in the case of the stellar mass, the error almost doubles. So without redshift is 0.06, and with redshift is 0.06, and without redshift is 0.12. When I go through here, yes. So if I take out the redshift as an input, if I just give the 12 magnitudes, what will happen? And that's what happens. When I remove the redshift as an input, you see that the error almost doubles. So it's very good to consider the redshift as an input. So something else that we did was a Fornex cluster application. So we took a sample of about 300 galaxies from the Fornex cluster. We took only galaxies with all of the magnitudes with no missing data. So this ended up with 182 objects. This is a very old application that we did. But what we tried to do here was to estimate. So to make some color plots. So on the left side, you see the color age diagram, and the x-axis is the G minus R. So as you go to the right, it gets redder, and in the y-axis is the age weighted by flux that was estimated by our model. So we asked our model, here are the galaxy components, and we wanted to give us the age, for example. And so to create this color age plots. And we see that there is a relationship that we expected. We expected as the galaxy gets older, it gets redder. So as it gets up, it goes to the right. And that's what we see, a linear relationship. So, and on the right side, there is an age metallicity plot, which is the same way as this one. So we asked our model to obtain the age and the metallicity of the galaxies. And we also see a linear relationship. So basically, as the galaxy gets older, the metallicity gets higher, which is also what we would expect. And so what these plots are showing is not something new. We knew, or at least we expected this to happen. This is what we call a sanity test. So even though our relationships are making sense statistically, the errors are low and things are going well when we look at it statistically. We wanted to see if our model is predicting things physically okay. So the physical relationships that we had are working out. And we see that yes, they are. So we were pretty happy with that. Something else that we did was the BPT diagram. So the BPT diagram is this diagram over here. So it has on the x-axis, it has the N2 over H alpha line, and on the x-axis is the O3 over H beta line. So the BPT diagram is for galaxies and has this two-winged shape. So you can see that there is a wing over here and a wing over here. And the nice thing about the BPT diagram is that we can talk about what is the population of the galaxy based on its position of the diagram. So you can say, for example, if a galaxy is AGN, is quiescent, start forming, based on the BPT diagram itself. And so on the left side, we have the BPT diagram obtained by the STARLIGHT value. So the direct STARLIGHT value. So this is kind of the true BPT from STARLIGHT. And so we try to get the same galaxies that are in this diagram, and we asked our network to predict both the O3 over H beta lines and the N2 over H alpha lines to create our predicted BPT diagram. And we see that even though the scatter isn't the same, so we don't see the same scatter, for example, for the right wing of the plots, we still have the same two-winged distribution. And the important thing is that the positions of the galaxies which are important for us, for example, for saying if it's the left wing or the right wing are still the same. So we ended up pretty happy with that, because the idea is that the continuum of the spectrum gives us some information about the formation, the star formation of the galaxy. And so the last thing that I want to talk about, I promise this will be very quick, but is one of the ways that even though our model are estimating very well, we are pretty happy with the results, we wanted our model to give us an idea of the specific error for each one of the prediction. So let's say, for example, I give it a new galaxy, and I want the model to tell me, oh yeah, this galaxy that, for example, has a very high redshift or some very high magnitudes. It's a very faint galaxy. It has a higher error of the prediction when compared to other galaxies, to brighter galaxies. We wanted to have a notion of error for each single prediction instead of a notion of general error of the network. And so one of the ways that we try to, there are a lot of ways to try to implement that by using, for example, Bayesian networks. The way that we tried to implement was by using something called the test time data augmentation. And how that works is, for example, let's take this simple pipeline of how a machine learning code works. Let's say that you want to make a classification between cats and dogs. So you want to give to the network some image of a cat or a dog, and you want the model to tell you if what the image represents. So you, when training the network, you have a training set, and you give those images to the model, which will train for a very long time. And so the prediction, when you go to the prediction part, you take a new image, for example, of a cat or a dog, you go through the training model, and you give you, for example, a percentage. So say, for example, yeah, this image has a 90% chance of being a cat. What time test data augmentation tries to do is try to change a little bit of the pipeline. So the training set, the training part of the model continues to be the same. You still train the same way. You give the network the same training set, you train for the same model, you train the same way. But the prediction part is where it gets interesting. So the idea that whenever you give a new prediction, you want to make a new prediction. Let's say, for example, that you want to predict this image of a cat. So when you give it to the network, instead of giving just this image, you will try to modify this image a very large amount of times. So you give, for example, you try to rotate the image, you try to flip the image, you try to mirror the image. Each time that you change a little bit the inputs that you try to predict, the network will give you a different result. So for example, for the first image, you say that's a 90% chance, or 89% chance of being a cat, then 87, then 92. And the idea is that if you do that a lot of times, you actually manage to have some kind of probability distribution. And so you will have some kind of notion of error of the network. You get some idea of, oh yeah, this prediction over here has a probability of being the mean value of the distribution is this one, but the standard deviation, for example, of the distribution is something to consider. So we expect that for fainter galaxies, for example, we will have a larger bell. That's the idea that time test data augmentation will try to do. And just to see this in action, so we try this for a single galaxy. So this is one of the, it is a very pretty name. So IT0073, blah, blah, blah. We try to use this method that I just described before for both the stellar mass and the velocity dispersion. And so we changed for this single galaxy, we changed the magnitudes just a little bit, 105,000 times. So for 100,000 times, we tweaked the magnitudes and the redshift, and we obtained this kind of distribution. It has the same, so it has a mean that we expected, but we can see that the data has some kind of notion of error right now. We know, for example, if you take, we expect at least that if you take a fainter galaxy, for example, the distribution will be different. We have a notion of the error for each single prediction. And yeah, I think that's it. I'll just go over very quickly about my conclusions. So we managed to train a neural network that was capable of estimating 9 stellar population parameters directly from S+ photometry without going through all of the SED fitting parts. And in the future, we want to better estimate the error of the prediction, which is the part that I just talked about. We want to increase the redshift range, so we want to go further than 0.1. We want to compare our results to other S+ SED fitting codes. So even though that it seems that we're working our work is doing a very good job, we wanted to make sure that compared to other codes, other classical SED fitting codes, our results are similar. And we already gone through this step. We checked with other groups that are working with S+, and we saw that the results are very similar. So my machine learning code is doing as well, if not better, than other classical SED fitting codes. And we can consider in the future using some other service to give us more data to the network. So consider not just the S+ magnitudes, but use, for example, the Ys, the galaxies, photometry to give more data to the network. And we want to publish these results. And I think that's it. Thank you.
What are your measurement inputs? You need the 12 band measurement, or there is a limit of bands? For example, you can only use your code object that have 12 band or not.
I think you're asking about missing data in the case of missing data, for example.
Yes.
So no, you can actually work with missing data. That's not a problem. So you need to give the network some information, and we usually give that information. We give a value to the network, for example, 0 or 99, just to tell the network, oh yeah, this value is missing. But
it works well.
And it works well. Yeah, it works very well. I tried the same plot with so that I showed with Fornex. These are just galaxies without missing data, but the same plot, considering all the 300 galaxies with missing data, is just as good.
But there's probably a limit of features you need to these, I imagine.
Yes.
Do you know?
I don't know, but looking at S+ data, we see that I think 80% of the galaxies fall between 1 to 2 missing data. So for the galaxies that have missing data, most of them are concentrated between just having only 1 or 2 bands missing. So I don't think there is a limit. Our model will get worse as we increase the number of missing data in the prediction.
That, for example, without broadbands, for example, would be bad, would be worse.
because you need some narrow bands in the blue part of the spectrum. Maybe it's not so bad and regardless. But
Yeah, that's a good point. I don't think we actually try to study how the missing data affect the network
no.
by looking at each one. Yeah, but that's a good,
Yeah,
an interesting point.
The errors in the photometric redshifts. How you put accounts for that? No.
Yeah, so the errors of the photometric redshift is something that we're very interested in. So that's why we try to, so of course, photometric redshifts are quite hard to estimate, and they do have some considerable error. For example, in the case of Fornex, I guess the photometric error of the estimation is similar to the redshift of the Fornex cluster. So we do try to take that into consideration when we do this, the test time data augmentation. But it's certainly something that we need to try to tackle more. Right?
When we apply sort of technique for galaxy, we know that all galaxies are the same redshift. So you can impose same redshift for every galaxy. And so in the case of the cluster groups, etc., this method is very powerful and this is not at all. Of course, for the field in general, the effect of photometric redshift is to lure the large scale sculpture. Then we have another project by another student that is they convolute the photometric redshifts in order to recover the original galaxy distribution, which is very good.
To second the problem that I just remembered that you told me before about the missing data on the specific bands. One of the ways to see that that is by computing a feature importance. So if we actually know what's the importance of each one of those features. So for each band, for example, how important they are for estimating the output, we can have an idea of. For example, if there is a missing data in, for example, the age alpha line, just the output is way worse. But so we actually did some feature estimation. I think it was the last thing that we did before coming here, but I didn't include it in the slide. But you can actually see that, if I'm not mistaken, the blue region is the most important, and then the red broadbands. And
regarding the missing data, usually the internet world
yeah.
Then we miss one of the picture. You need another driver network. Then you have
No. You just that's true. You don't need you cannot run, for example, this network without passing some value as inputs. You cannot try to run this by excluding the magnitude 1, for example. But what you can try to do is just input a value and like mask a value as a missing data. So for example, let's say that we don't have the magnitude 12. So I'll just include, for example, a 0 over here. I'll just give the network and say that, oh yeah, so this value, instead of being missing, which is I don't know how S plus deals with, I don't know if that's none or if it's another value, but we just give the network one value that we specify as a missing data. So we say that's 0 or that's 99 or minus 99 or whatever you want. But yeah, you need to give the network some kind of value. Yeah.
It's a very interesting point. But if you put a data, I was saying that we have to work with that the universe will not ever produce. You have to work with learnings that these values is. This is the point. And so it provides reliable results using only the other network.
This is normally something that you need to tinker a bit with. So it's not like a usual a universal law. For example, you always use 99 or always use 999 or whatever you want. you usually need to change the values and see how the network performs on each value of missing data that you go through. So it was actually something that I talked about with Claire some weeks ago, was like trying, instead of using, for example, 0 or 99, using other values and see how the network performs on those values. But yeah, it's something that you need to consider.
So there is a problem when you were saying that Tesla is China and relation to everything on together. So I thought you would, when you show this picture, then I thought really that you would say that you had protected your image and the galaxy is the same. You know the parameters to be the same, but then you said that so you didn't do that, you didn't protect the image, but you just change the magnitude of it, right?
Yes, yes.
Okay. So then I thought about the diagram, in which you say that actually you are predicting a much narrower distribution. The dispersion in your prediction is lower than the actual data.
Yeah.
So when I saw this plot, I thought, okay, why this is happening? Is because your model is maybe over predicted, and you in different values you will still get the same prediction. So you're not predicting like the broad distribution of nature, but much narrower. So that was one question, and the other one that arises to me when I saw the last slide was, okay, does this have to do with the prediction that you get for the errors? In the sense that if you vary a little bit the magnitude and you get a difference in the prediction, okay, but maybe because of this narrower distribution, you would get a similar prediction when changing the magnitude, you would get a less different solution, more similar solution. But because from the beginning your network was just tending to be almost always the same answer, you know what I mean? So is this estimation of the error a result of the fact that your network is tending to give the same answer than the small dispersed?
I just see if I understand the last question, sorry.
You don't know, because if you go back to the release, if I don't understand now the other one, this is reality and this is prediction.
Yes,
right?
yes.
So
Just clarify.
yeah,
The network, the input doesn't respect, sorry, how to say, the models that we are feeding the networks don't have initial. The network is predicting each other. On the other side, the observations, because we are working with that spectrum, not the spectrum from Rosdor. And this contains only the continuum. On the other side, we know that, say, blue spectrum contains additional lines, red spectrum in general not, that they are AGNs. But then we decided to verify whether the network is able to predict the initial lines and their properties, the particular equivalent, and it does. So the network doesn't see anything about the initial line, and but they predict that the equivalent width of the initial lines if the spectrum is that one. Regarding the question of errors, this is much more complex. Let me see. Let's suppose that we have something like that, is error bars. And we want to make a model. And if we obtain a given observation X, and we want to estimate Y. Okay. You can imagine that there are many possible solutions for this problem. For example, I can do a linear regression and obtain, say, something like that, and this will give me a value of Y. On the other side, I can take, when I do a linear regression this way, we minimize chi-square like that, consider the errors in this way. Okay? This is the classical way to do it. But I can think also of the following. I can do lots of simulations where for each data point, I assume that the errors are Gaussians. Is the same essentially. And we can sample from each point according to a Gaussian distribution. And we will have another value of epsilon of Y for X that I call Y2. Will Y2 be equal to Y1? Well, this is a kind of situation where we need to think about how to deal with the errors of the observers. This is one point. But another point that's more complicated is the error in the models. I assume here a straight line. And what happens if I have assumed a parabola, for example, or any other thing? So, when I obtain an estimate for Y, somewhat I need to include both the errors in the observations and the errors in the model. And this is an open question in machine learning. This is one of these areas where most work is being done. There is an approach that's called the Bayesian neural networks that use some technical things like dropout, where you exclude nodes.
Each node isn't represented by a single number, but it's a probability distribution. So it tries to train different signs, and each sign is sampled from those probability distributions, and it tries to get a notion of the error of the model.
So my point is the following: the question of the errors in the learning is over.
Okay, that's
This is the short answer.
but he was referring to that. That's
Yeah, he was showing this sampling from the errors in the observations. Assuming that the model is correct. But it is also possible to include the errors in the models. That's why that's what the Bayesian networks they distinguish between statistical errors and what's the name of the
Stochastic and random.
No. They give a name, a specific name for the errors in the model. No. I have to. I will discover that you
More questions, Claudia?
Yes, I have another question when you talk about calibration, that you said that. So if I understood correctly, this 137,000 galaxies are observed and several measure the spectrum and whatever, and estimate what would be the photometry with the splat and then compare with those subsets that are splat catalog, comparing with the.
Yes.
And you say, okay, I calibrate. So I don't know here if you are considering all the steps, like the variables, the redshift. Yes. So if you do that, there are particularities in the spectrum that are coming from, for example, that they are redshift or that they are different galaxies and the spectrum are different. So what I'm trying to say is how, if any, how did you take into account the particularities of this galaxy
Okay.
into the calibration? Because I mean, this is like a mean calibration with the 2,000 galaxies. No, you 6,000.
6,000. Yes.
6,000 is an. I don't know if you understand.
Yeah. I think I do. Yeah. But yeah, usually when we do this calibration, we do by redshift beam. So I think that's probably what you're used to seeing. Like you calibrate, like for example, galaxy between 0 and 0.1 and 0.1 to 0.2. But in this case, we have such a small redshift range that I don't think we need to actually think about the redshift dependency between 0 and 0.1, for example. The change will be so small that it won't be apparent in the calibration. So basically, we're calibrating the 0 and 0.01 objects the same way.
Okay, so then you trust that new galaxy, you will calibrate.
Yes.
Because you want to go from the splat to the real or the other way around.
Yes, we want to go from the synthetic data to the real split data. Yeah.
From the synthetic to the
Yes.
to the splat. I mean, where do you compare? Because so I had taken note, but then I forgot the line, the clock line. Because okay, yes. Now I don't know. You go. You did this calibration. You apply from the synthetic to a splat.
Yes.
So you have.
Yeah.
Here the models are called Epstein.
Oh, no. Okay.
Any more questions?
Yes, do you include some information about the morphology of the galaxy?
No, we just.
We don't remember the sample of Ariel.
Yeah, they are just spectral. They're just the starlight spectrum. But no, we don't include any information about the morphology because I don't know if there is a pipeline in S+ to obtain the morphology parameters from the galaxies.
No, but we have the morphology of all Ariels.
Yeah, we do, but I don't know if we can do this when we go for real.
That's
Yeah,
morphological classification using the precision of the result depends on the morphology of the galaxy. Whether the
yeah, because
are very different.
I think we could increase the range of features for a lot of other things. We could consider the morphology. We could consider even the position if you want, or other magnitudes. But I don't know. It worked with the magnitudes, and but yeah, we could expand to.
The sampling in time and data galaxy.
Yeah, that could work.
Photoshop is open. Or with only the photometry predicting by the recognition.
Yeah, I don't know if that will work, but I think we can try.
I think it works. When we have used
Yeah, one of the things to consider is that I was talking to Larry yesterday, was to include, for example, the image of the galaxy when in the picture. So instead of just passing, for example, the 12 bands as a single value, for example, try to pass the image of the band. And yeah, that could work. There are some photometric redshift estimations using this, but it's a lot more work because you need another type of model, and it takes a lot more time to train, and the data is I never dealt with images, so
I think that the most important thing to do is to train all parameters simultaneously. In this case, the architecture of the network will be able to somewhat be more robust if it has to predict stellar narrative at the same time.
yeah, I try to predict all the parameters at the same time. So, but I don't know, maybe for this specific architecture that is the one that I use, the complexity is so low that it didn't manage to, by predicting all of the parameters at the same time, the results were worse than trying to predict them separately. But something else that I tried to consider some time ago was to, for example, if we know that there is some kind of correlation between the, let's say, for example, the age and metallicity of the galaxies. And so if you know that there is a high correlation, and if we know, for example, that the age of the galaxy is estimated very well, and the metallicity is not that good, so what we can do is try to estimate the age and use the estimated age as a feature to estimate the metallicity. We first estimate the age, and then we take that age and input as a feature to estimate the metallicity.
So this, at this point, you have done a different network for each of the.
They are all the same architecture, but they are trained separately. Yes. So
This is a very simple architecture. This is almost the hello world architecture.
Yeah.
You know,
and it's seriously,
he would complex architecture. I don't know, we have so many things to do.
Okay. Now we also. So, but this, have you changed the details in the architecture?
yes, the hyperparameters of the network. Yeah, I changed the number of layers, the number of neurons, and I had a very extensive grid actually, and the best result was the simplest one. So the best network out of all the ones that I tried was this one, the simplest one. So I think I tried up to 10 layers of 10 hidden layers, and up to I think 1,000 neurons per layer. And I don't know, the best result was this one. So I just went with it. So I don't know if the higher complexity I had to train for such a large amount of time that I didn't get there, but I don't know. But yes, I tried some optimization, and this was the best that I got.
Did you try train neural network combination?
Yeah, this is, I think, very common, especially, I think, when they are estimating photometric redshifts in S+. I think Eric uses the color instead of the value of the magnitudes. And Raquel, which is trying to estimate for quasars, is also doing. And I tried in the beginning to instead of using the value of the magnitude, use the colors, but the result didn't change that much. But so I just went with the magnitudes instead. But yeah, you could consider using the colors instead of the magnitudes itself.
Going back to the missing values.
Okay.
Here, I was thinking about the real put the -99 and the network recognizes the particle. When you train the network, you put missing value in this training.
No, we don't train the network with missing data, but that's something that we consider sometimes. So a couple of months ago, I was studying this problem of missing data and what values to use, what to consider. And yeah, I talked to Lars about trying to train the data set, the training data set, to have the same distribution of missing data as the S plus observations. So
you need to, in order to the network to recognize missing data, you need to have missing data in your training set. Otherwise, you have.
no, it will give you out some output, but
Yeah, to always give back. If it was not trained with missing data, it will not give proper answers.
no, in the case of photometric redshifts, the missing data is used. So Ed, for example, doesn't use a value, for example, for 0 or 99 or any other thing. It uses the maximum value of the filter. So instead of using, for example, 99 for the magnitudes, so let's say for the blue band, it doesn't have the information. You use, I think, 33. I think it's one of the highest values that you got. So it will just use the maximum value. And in this case, I don't think you need to train the data previously with those.
The network learned what to give you. If you want to learn the missing, how to interpret properly the missing data, whether if you didn't feed it in the training process with missing data.
Yeah, but in the case of magnitudes, you do have like the higher the magnitude, the fainter the galaxy, right? So the idea is that the higher the value of the magnitude, the less considerable should be that magnitude.
What you said is true, but I don't think that the result will be good.
Okay.
You will want to use this data in training.
We would prefer to map the values that are in the lower.
We don't use math, we do the data and represent the missing data. You can consider it a kind of math. But anyway, I think that in the case of Eric, it includes the trends or from one way or another, maybe using the maximum value.
Yes.
But you know, you can't expect that a network trained with good magnitudes will understand that 99 that appear.
Oh yeah, of course. That's why I don't talk about 99. I talk about the maximum value of the filter. Yeah, you should consider.
If you want that the network learns how to
recognize it.
Yes. Because in general, we like complete photometry, and we train this photometry and apply this complete. That's it. In general, what we do. By the way, I remember the year that the year the models are called the twice. Epistemology.
No, I need to listen. Thank you very much.